Hi, I had a viewer email me about a circuit that they were having issues with, and they wondered if I could help out, analyze the design and PCB and tell them, if they're doing something wrong, what's happening, explain why they're getting issues. And I get emails, a ton of emails like this all the time, and unfortunately, I don't have the time to respond to most of them. So I usually say, look, it's better off if you put it on the EEVblog forum, and then either myself, because I'm a forum nerd on the top poster over there, or thousands of others, tens of thousands of other engineers on the EEVblog forum can help you out. And then you get much more input from everyone, and everyone discusses it, and everyone learns everything, and then it's searchable from the public, and it's all fantastic. So yeah, rather than just give a personal reply, I thought I'd do a design review video. And if you like this type of video, give it a big thumbs up. Please leave it in the comments down below, and I might make this possibly a series, although I don't want to get inundated with design review requests. Anyway, I thought this one, there might be some interesting things to talk about in this one. So thank you very much, mlyman89, for providing the easy EDA files that I or anyone else can go in and have a play around with. So let's check out his email, shall we, and see what's what. Hello Dave, I'm a big fan of your YouTube channel. I recently watched a video explaining PCB design of a photo sensor because I can't seem to figure out how to design a PCB properly and was looking for video explanations to help me. I'm having some PCB troubles of my own and thought maybe you'd be able to help me figure things out. Well, I can give it a go. I'm a total novice and do not know what I am doing, but I'm trying. Awesome. Anyways, I'm trying to create a PCB with two 74HC595s. You know I'm a 595 fanboy, and two ULNs 2803s. I'm also a 2803 fanboy as well, to control a SaneSmart 16-channel relay module with my Raspberry Pi. I'd like to be able to daisy chain multiple of these PCBs to control multiple relay modules. I have prototyped the design and it works well on a breadboard, but when I had the PCB built by JLC PCB, I'm getting very unexpected results and can't seem to figure out why or how to solve it. If I use just one PCB, it works. No problem. But if I daisy chain more PCBs to use more relay modules, it doesn't work. Well, it still works, just with unexpected results. Aha! A lot of experienced engineers might already twig to what's going on here. But anyway, let's get into it. Like, two relays will be triggered when only one was supposed to be triggered, or the wrong relay will be triggered. My goal is to create a firework firing controller. I know, super original. No, it's good. Do it. The 74HC595 datasheet says to use a 10 nanofarad cap on each chip, and the ULN 2803 doesn't specify needing any capacitors. The PCB will connect it directly to the relay module with a 2x10 female header block using the 5-volt ground supplied by the relay module to power the PCB. I was hoping you might be able to take a look at schematic and PCB, where my mistakes are. I think we might be able to help out here. Okay, first of all, let's have a look what's happening here. He's trying to connect this board to one of these SaneSmart 12-volt relay modules. So a whole bunch of 12-volt relays and what looks like optocoupler inputs. And here's the header connector that he's designing the PCB. Where is it? I had the PCB up. And this is what the PCB is going to plug into. So there's his PCB with his two chips and his input and output header connectors, where he's going to potentially daisy chain them together for multiple relay boards. And yeah, so that plugs directly into there. So no real signal integrity issues or anything else really to do with interconnecting that board to this module. It just plugs in that header, gets power from here, has a local regulator on here like this. But the interesting thing here is that this has been driven by optocouplers. They're classic optocouplers there. And even down here, it tells you, where does it tell you? It tells you something. More info. 12-volt, 16-channel relay interface board, and each one needs 15 to 20 milliamps driver current. So you need significant driver current to actually drive the optocouplers on this board. You've got to drive like that, 15, 20 milliamps through the lead in the optocoupler. LED. A lot of people complain about lead. No, it's lead, damn it. Not LED, lead. So you've got to drive the lead with, a reasonable amount of current to then saturate the photo transistor on the other side, which then switches on. It looks like it. Oh no, it looks like it has receivers. Anyway, the manual doesn't download on here. I don't know why, but I found an equivalent one. I don't know who's ripping off who, but it looks slightly different. The regulator looks different and stuff like that. But anyway, so they've just got, looks like just some optocouplers driving once again some ULA 2803s. If you don't know what they are, well, I'll show you. It's a Darlington transistor array. So it's basically just a logic input like this. So that'd be coming from the output of the optocoupler, the photo transistor, and then they've just got big, beefy open collector transistor in there, which can drive relays and, hundreds of milliamps. So 500 milliamps. There you go. You can get different variants of it. 50 volt output voltage, grunty, right? Great little things. And they've got a reverse protection diode in there. Great for protecting you from back EMF from relays, for example. So you don't need the external catch diode for the relay. Great. Anyway, once again, this says it needs 15 to 20 milliamp driver current. So unfortunately, we don't have a schematic or anything for this. So I can't tell you what the optocouplers are, whether or not they need less current or something like that. But that seems to be the specification. So these are not designed to be driven by a digital interface. It would have been better to pick a board that actually had a digital interface, and then you could go directly from, if we go over to the schematic here, you could do away with the ULA 2803s here. You wouldn't need them at all. You could just take the outputs of the 595s directly into the relays. So, okay, so all we've got is a board here with a header, which is powered from that SaneSmart relay driver board. We've got some 595s, which, if you don't know, is a serial input shift register, one of my favorite chippies. So basically what it's got is a serial data input that goes into the input data of the first flip-flop here, and that's just got cascaded flip-flops like this. So, and they're all then clocked from a serial clock like this. So you can feed in data and a clock, and you can feed, if you feed a 1 in here, then the 1 will go from here, and then the next clock cycle, the 1 will transfer to here, then the 1 will transfer to here, and it shifts along. So you can shift data in. And that's why the 74595 is just the jelly bean part for doing I/O expanders. If you've seen my oscilloscope teardowns and stuff like that, you'll see one of these inside the front end, for example, in lots of Rigel scopes, all the Siglet scopes have them. Very common, because you only want to have a couple of, you don't want to have, if you've got like 8 control lines that you need for controlling various things in a front end or any other part of your circuitry, then you need 8 lines coming from your microcontroller, and that's kind of annoying. You've got to run them right across the board, and you may be out of pins on your micro or whatever. So this is like a serial expander, so to speak. So you only need 2 lines like this, and then you can cascade as many chips in series as you want, because it has a not QH output here, and then that can then cascade to the data of the next one, and you can 2 lines can have as many outputs as you want. So you just shift in the data, and once you've shifted in the data here, then you do the R clock, which is the register clock, and then you've got another bunch of flip-flops here, which then transfer all the data out. So all the data can actually shift out all at once. So it's all synchronous, because if you're trying to clock things and do other stuff in your circuitry, it takes time for because your clock rate is it's a certain clock rate, and it takes time. That's a terrible looking waveform, isn't it? It takes time for the data to shift through all of these registers. And if you don't have, you can get versions of these chips without these registers if you want. But then the problem is that these outputs here are just constantly changing all the time as the data shifts through, and you don't really want that. You want to make sure the data is in the right position first. So if you want 1 here and a 0 here and a 1 here and a 0 here, you shift all that data in first, and then you put a pulse on the clock line like that, and it'll shift it all through, and all the outputs change at once. Brilliant. Geez, I'm waffling on. Dave, you can get to the problems. Okay, first of all, nothing inherently wrong here, okay? So yeah, you've got some decoupling here, right? 100N, mentioned 10N before, doesn't really matter. You could put one big 1 mic on there, or one big 10 mic or whatever, something like that, which we might get into, because it might be part of the issue here. But anyway, yeah, basically, okay, if you've got a nice clean digital signal coming in, and you've got a couple of decoupling caps on your chip, as is basic, standard practice, then it should just, if all your edges are nice and fast, because don't use very slow edges like this. You don't want to use slow edges with your 595, because your 595, because your serial clock here and your register clock as well, they don't have what's called Schmitt trigger inputs. So, Schmitt, they don't have the symbol. If they did, they would have the little, well, I'll draw it out here, but they will have the Schmitt trigger signal, and I've done a whole video on Schmitt triggers and how they're better for if you've got dirty clocks coming in. If you've got dirty, filthy clocks, because if you've got a clock that's coming in like this, and, it's got some filthy bugger business going on here, right? And it dips down like that, then you can get multiple clocks. Anyway, if your logic thresholds are like this is the worst diagram I've ever drawn in my life. Anyway, they aren't really set thresholds. So, or if your data transitions really slowly, as I said through here, you can get noise on your signal. Noise like this, and noise can, right? Got a dirty, filthy, noisy signal like that, that can actually cause, depending on the threshold levels and everything else, or the fact that it's in no man's land in here, that can cause multiple triggers or multiple clocks on your input here. So you may have intended to put one clock into here, but you end up getting a edge like that, but you get another little sneaky bugger edge in there like that, and then like that, and then you end up with actually 2 clock pulses, and your data doesn't shift into one position like this. It actually shifts twice through to here, even though you didn't intend to. And that's why we read here that like 2 relays being triggered when only one was supposed to be triggered, or the wrong relay being triggered. So right off the bat, I know for a fact that there's something wrong with the clock inputs here that's causing multiple clock pulses, and that's why you're not getting clean shifting of your data through the 595, and that's why you're seeing oddball stuff. You could actually add a Schmitt trigger buffer in here like this, and there we go. That's pretty crap, isn't it? You can add a Schmitt trigger buffer on all of your clock and data inputs here, so that it can try and clean them up and stuff like that. It's one method to do it. If you know your input, if you aren't certain what the signal integrity of your input clock is going to be, then at a minimum, like if they're coming from externally or something like that, you should be using at least Schmitt triggers inputs. Just to, if you've got noisy signals like this, that can cause a problem. So right off the bat, it could be noise, because this board, obviously, I don't know how you're connecting it to your, Raspberry Pi. So you've got the Raspberry Pi coming in. Your header cable might be, 30 centimeters long, could be half a meter long. We just don't know what that is. So we don't know the signal integrity of the clock coming into your 595. And I'm sure I've done videos on this. If you're going to scope this on your probe and see, am I getting multiple clocks? Then you've got to probe it correctly. That means not using this antenna earth lead, this huge inductor hanging off. Do not use this. This is not a proper like high frequency probing technique. You really need, if you're serious about signal integrity, then this just contributes to a big overshoot and undershoot on your signals, because it's got a lot of inductance in this wire. So you don't want to do that. You want to use the little ground probe on there and actually probe it properly, and you have to do some setup and stuff like that. I'm sure I've done that in many videos. Anyway, I won't explain how to do high frequency probing, but yeah, probing is important if you want to actually see the signal. You can't just hook up a scope probe loosey-goosey and expect to see it. So right off the bat, solving issues of like long transmission lines, essentially they are, right? Long transmission lines going from your driver board over to your receiver board like this. There's many ways to look at this. In fact, if you're going to be driving long things, you might not go for a single-ended solution like 5-volt TTL. So you might go for like a differential solution like RS485, for example, for driving stuff over long twisted pair lines. You might go for something like this linear technology LTC486 or something, which has, is a quad differential driver. So you have, digital in here, and then it drives a nice differential twisted pair terminated with 120 ohms on each end, and then it comes out here, and that's a really robust way to send digital data over very long lines. But in a situation like this, you may need something like that, but I won't go into the pros and cons of which solution to choose. And then there's other things about, terminating, you can terminate digital lines and stuff like this. I won't go into the whole signal integrity aspect of it, because that's a whole deep dive rabbit hole. I might have even covered that in other videos or something like that. So yeah, but there's something else in this that makes me think it may not be noise or something, and we have to go back here and talk about the thing we hinted at before. Each one needs 15 to 20 milliamps driver current. So if you need to drive like, 10, 15 milliamps per input that you're trying to drive, what 12 inputs or something? If you're driving let's say we've got 10 at 10 milliamps each, bingo, there's 100 milliamps or even 15 milliamps each. That's 150 milliamps right there that has to be provided by the power supply. And the power supply in this case are these two little piddly 100N caps up here. Otherwise, it's got to get it from the relay module over here, okay? And it's got to run all the way from, I can't point at it, damn it. But it's got to run all the way from the regulator there. It's got to run all the way over to the board over here. It's got to run through the header connector onto your board. But that's not a huge deal because this board, there's no cable between this board and the board. So the run it's relatively short. So anyway, let's have a look at the PCB here and see what's what. Please forgive me, I don't use easy EDA, so yeah, I'm not going to be able to do anything serious here. Now, it's using a 4-layer board here. So we've got VCC, we've got ground. Of course, you didn't need to use a 4-layer board like this, although it's probably going to help, as we're going to talk about in a second. And there's our bottom layer. Yeah, like why have a bottom layer at all? But then again, you wouldn't use like a 3-layer board, for example. You only get them in like even multiples. So anyway, yeah, that's a bit of a shame there. That anyway, top layer here, and like just before we get into this has nothing to do with the issue to hand. Just a few routing things, and I've done this in many videos, but I'm triggered. These traces coming out of here. No. Old school guys are going to be going, etch and trap. It's, yeah, not really an issue. These days, it's just an aesthetics thing. It's a professional layout thing. The trace should come out here like this from the center, and then 45 degrees, and then up, and then 45 degrees, and then across. Yeah, never bring them out from just inside like that. That's just a no-no. And once again, you've got like this, like going at an angle like that. That should have gone straight out to there like that. Yeah, you've done it here again and over here. For example, like I won't go into like clearance rules and things like that, but this shouldn't be this close to this pad. It should come through the center and then 45 degrees and then go through the center of here and then come through here and then down there and then down in there like that. But anyway, just a few little layout things there. But oh, and you've also done the ground here, like coming in the side. Oh god, that's annoying, isn't it? Sorry, I'm not on the ground layer. Yeah, it's like, oh yeah, it's highlighting the net. Okay, it's auto highlighting the ground net, is it? Yeah, I think it is. The tray should have just come out here and then dropped. Your VO should have been here and dropped straight down. Anyway, minor things. So let's get back into the actual issue to hand here. We talked about you could be drawing, if you switch all of these outputs on at once, you could be gulping hundreds of milliamps of current just to drive these output transistors here. So these are our shift registers here and our output transistors. So what we've got is essentially, this is kind of a neat example where while we don't have analog here, I've done videos talking about our separate analog and digital grounds and power supplies and things like that. This kind of shares a similar sort of thing. You've got a high power section, even though it's all digital, essentially, right? You've got a high power section here, right, with these two chips, and you've got a low power digital section over here. So if you're switching a couple of hundred milliamps, if all that current is flowing across your board through a trace or a plane or whatever that's shared by these little sensitive digital chips over here, you can get ground bounce, okay, and power bounce, right? You can get voltage drops in these lines. It's not so much of a problem when you've got a big ass ground plane in there. So I'm not necessarily saying it's an issue here. I'm just like, this could be one or potentially part of it, could be exacerbating the issue, right? You could be right on the margin with some other issue, and then this, not laying out your ground and power properly can, tip it over the edge and cause a threshold problem that we're talking about and the multiple clock pulses. So Yeah, so I don't think that's really an issue on this board. But the fact is, right, you've got your bypass cap here, okay? Yeah, it's via going down the ground and power plane. That's okay. Like, you know, if you're doing this on a 2-layer board, of course, you wouldn't do that. You would route the VCC track over to here as a priority to your bypass cap. You've only got 2 little piddly 100 end caps, which are fine for this digital side here, right? Or this low, call it the low power side, but the high power side, it's taking these huge gulps of current. Where's that current coming from? It's got to come, you've got no local bypassing on this board. It's not going to come from these bypass caps over here. They're on the wrong side. So really, the only place it's going to come is, where's the VCC pin? It's going to come from the VCC pin, right, through your VCC plane, of course, right, which is being shared by, once again, the ground and power. Even though it's a big, thick, low impedance ground and power plane, it is technically shared by the low power digital chips over on this side, and their ground has to flow and power has to flow basically under or through all of this high power stuff here. So yeah, when you're talking about couple hundred milliamp gulps, potentially that's, you know, worst case. You've got to always design for worst case if they all switch at once, for example. It's not just 15 milliamps of one switching. You've got to assume that they're all going to switch, of course. So that has to come from that regulator we saw over on the Sane Smart relay board. And how much bypassing do they have? Will it upset something on that board, for example? I don't think that's the case here. I think it's, you know, it's your issue's localized. I guarantee it's, you know, it's localized on the board here with the 595s. You get in multiple clockings in your 595s, guaranteed. But anyway, so yeah, what I would have done on a board like this is put local bulk decoupling. I'm talking, you know, a couple of 100 microfarads, where, you know, significant current here that has to be gulped, and you don't want it to come. It's pretty rude, quite frankly, to force it to come from your other board. And this would be especially a problem if this was a long line. If you had, if your board was here, you had a long cable, like a ribbon cable connecting over to the board over here, those big gulps of current would have to come through the really thin cable over here, which is once again being shared by these by these low power ones over here, and then your ground and power is just bouncing all over the place because it's drawing a couple hundred milliamps in. You know, you might only be talking, you know, tens of millivolts, you know, bouncy drop or whatever, but, you know, you can really come a gutser from that. So anyway, yeah, and then it rings and does, like, it'll resonate and you can get big ringing and all sorts of issues. But the good news is that, no, you're plugging directly into the board. So I don't think it's a huge issue, but this board should have a couple hundred microfarads. I'd probably have one for each chip, for example, or even one bulk. And then you actually run separate traces. So can we actually place a track, W to place a track? So let's place it, well, let's assume it's a big thick trace, okay? I won't bother changing it. But yeah, then I would have a cap in here, right? A big couple of 100 mic cap, okay? And then I would power the VCC here like this, and I do, like, you know, you got to get routing room to do this, but then I would do either share it. Like, you could go, W is it? Yeah, you can share, I can't go across a trace, but then you could run it all the way down there. You could run it on a different bottom layer or whatever, right? And then pop it up and power this chip, right? And then you want your power over here. You want to separate these. So you want to actually, you could actually split your power plane. So the VCC could actually be split. Yeah, I don't know how to split a power plane on here, but yeah, you could actually split the power plane and then have the power for just these, for the low power stuff, coming around here and going back to the pin. So you're effectively star powering. It's called a star because the traces go off in, you know, it's one central point, and then you've got digital stuff, you might have analog stuff, then you might have high power stuff going off, and it's all from one central location. And then you'd have a big bulk decoupling cap just for that as well. So I would potentially, because we're talking a couple hundred milliamps, it's good design practice, you'd put, like, you know, you might have 100 mic decoupling for these, you might have a bulk 100 mic for the board or something like that, and then, yeah, and then separately run these analog ones back. But because they're ground and power planes are pretty low impedance, it's probably not an issue on this board. It's just something to think about, or it could be combined with other issues. After having said all that, I just realized that, yeah, these are actually open collector outputs. So all the currents actually, it's not being supplied by VCC here. It's actually being supplied through ground. Where's the ground? up there. Yeah, it's actually being supplied through the ground. It's being supplied on the power on the optocoupler side over on the board over there. But still, the current is got to flow through the ground, back to the other board. So it's a similar sort of thing, but it's not as bad as a full loop coming through the VCC here. But anyway. Okay, so let's say we have our board over here, okay? And this has our driver on it. That's our 5-volt digital driver. And then we've got our ground as well, okay? Because your ground is going over. So your ground's going all the way over to here. And you've got ground on your receiver board here. So this is the big cable that you've got connecting this thing. We have no details on that, okay? So this has to come over and this has to drive your serial clock line all the way over here like this. Now, you could actually probe this with your scope and find that, at the output here, you have a beautiful, nice square wave, something like this, okay? Well, by the time it gets over this dodgy transmission line, which luckily you're not taking that 150, that 100 milliamps, 10 to hundreds of milliamps gulps of current from this board over here. If you were, and it was going over all these lines, and you get massive bounce in your ground like this, and yeah, that would really ruin your day. But luckily, you've got it coming from more locally from that relay driver board. Anyway, but by the time the signal gets over to here, it's not going to look nice and square. I'm going to expand it here. So let me expand it. This is the clock line. It's going to look something like my horrible drawing here. It's going to have lots of ringing on it. Okay. And then when it goes down here, you're going to get undershoot. And it's going to look something like that. Okay. It may be as bad as this, it may not. Actually, I guarantee that the clock going into here, if you're able to measure it properly, is actually doing something horrible like this, and you're getting multiple triggers. So if you're just, crudely, if your logic threshold is like this, then you're going to actually get a signal that looks out of, basically out of here, out of this buffer here, because this is an input buffer, okay? It's not Schmitt triggered. So you might get a signal that now looks, I'm going to try and time correlate this. It might have a short little pulse in there. Could have a little runty or whatever, but yeah, it's going to look like that. And you're getting this extra pulse. You're getting one pulse here that's being clocked in because is it positive edge? Yes. So if you get it, yeah, positive input, positive edge here, your data gets clocked through on the positive edge. So data gets clocked here, but then it also gets clocked here. And unfortunately, you can't actually probe inside the chip. If you probed inside the chip and probed the output of this buffer here, you would actually see multiple pulses there. You'd actually see these pulses. You wouldn't have to worry about signal integrity because it's already buffered by this chip here. So you might be able to actually see that if you actually insert an external buffer in there like that. You get your dirty signal. If you can't measure your signal integrity properly, you could have, if you had a buffer in there, then you could actually probe your output here, and you'll be able to see if you're getting multiple pulses. Anyway, I guarantee that is where you're getting, that's your problem. You're getting multiple clock pulses inside here, and it's shifting your data through more times than you expect. It could be a software timing issue because, right, this is positive edge triggered, okay? So this clock here, on the positive edge here, it clocks in your data, okay? Then you got the negative edge and you got the positive edge again, and it'll clock in your second data. Let's say that you wanted to clock a 1 into this, right? So you got a 0. Your data should change like in this part of, it should change in the middle here somewhere. So then it's 1 when this goes high. When you want it to be clocked in like this. This is called setup and hold time. And you can find this in the data sheet, and you'll find that there are setup and hold times for this. So this gets into timing analysis and stuff like that. We're not talking about signal integrity anymore. It could be any one of these things. Oh, by the way, here's these rise and fall times I was telling you about before. Do not exceed like at 4.5, I don't know why they don't give 5 volts, right? 4.5 volts. Do not exceed 500 nanoseconds, because if you do, you can get multiple. If your input clock is too slow, like if this is common on I2C buses, for example, because they're an open collector output, so they need a pull-up resistor, and if your pull-up resistor is too high, the capacitance on the line, it can cause slow charging up like that. And if your time from here to here is greater than your 500 nanoseconds rise and fall time, you can Kamagatsa and you can get it can enter metastability. You can get multiple clock pulses. Basically, nothing's guaranteed anymore, especially driving flip-floppies and things like that. You get metastability. I've probably done a video on that. And you can get multiple clock pulses. It could ruin your day. Multiple clock pulses, okay? And here's the input logic thresholds. Once again, I've done videos on this. So you've actually got this region between 1.5 volts and 3.15 where it's an indeterminate region. So if you've got overshoot or undershoot, that's causing ringing, and it goes in this region, especially if it takes some time, for example, then yeah, you can get, that can cause you multiple clock pulses. But here is our setup time, okay? So what we need is SIR, which is, I believe that's the serial data, is it? Yeah, serial data in, so the data in before the serial clock, it's got an up arrow, that means the serial clock going high, because it's an active high transition that it latches the data on. The setup time is typically, because this is a, 74HC, this is the military version, the 5.4 series, at ambient temperature. It does vary over temperature, so if you're right on the edge, might work in your lab here, get outside in 40-degree heat or 0 degrees, and you Kamagatsu, it doesn't work anymore, because you're right on the margins of your timing. So anyway, at 5 volts, you need 25 nanoseconds setup time, so, which isn't much, of course. That means that your data over here can, go high, right, just at least 25 nanoseconds before that positive edge comes along. Well, my head's in the way. Before that positive edge comes along there. So, yeah, that's, but, these are all things that you need to consider for even like a basic design like this. There's, you can really go down the rabbit hole. Trust me, I could do a whole series on just implementing something like this. It's just, there's so much to it. But yeah, setup and hold times. But so there could be a software problem. You may be setting up your data. It could be as simple as that. Look, you're outputting your data at the same time as you're clocking it on the edge here. And if you do that, might work sometimes, might not work at all. It's, it's just, yeah, not good. So yeah, you want to set it up on the negative going transition of your clock pulse. And then, of course, we have to think about that you're potentially daisy chaining these together. And you said that, the issue starts showing up when you daisy chain many of them together like this. Now, you could actually have a driving problem due to the capacitance of the line. Because if this is your Raspberry Pi board over here, if you're driving one module, it can be okay. Your signal integrity is okay, and it's working fine, but you might still, you might get the occasional thing. But then you need more lines coming down here like this, which goes off to, another board here, right? So this is the identical board, but stuck in here. So you've got your 595s and everything in here. And then, you've got the output of this one plus, right? So you got the output of this. So this combines back in here like this and like that. And then this goes off to your next board like this, daisy chain like this. And you're daisy chain these boards. You've got the one driver over here. The one driver may not be enough on your Raspberry Pi to actually drive all of the capacitance of all of these lines. So once again, that could slow the lines down. Slew rate can drop the voltage level. That drops your voltage margin, your voltage level margins on your chip. And bingo, you start getting maybe progressively as you get along the chain like this, you might find, that the ones near the end of your chain don't have the margin required for clocking in everything successfully. So what I would do there is have another, a buffer chip on this board that then drives the output of the board. So yeah, this is your input over here. Yes, I believe it is, right? So this output here, I would actually have another set of buffers, right? Just buffers or, 2 inverters in series, whatever, to drive that line, because otherwise you've got this one clock line here. This poor little, oh, you've got the clear as well, have you? Okay, so you've got the register clock, the shift clock, and the clear. You don't necessarily need the clear line, because unless you want to like clear things really quickly, you can always just shift zeros into it. So, you know, I've saved, I'm using 595s, I've saved an extra line by, you know, which can make or break you, saved an extra line by not requiring a serial clear, because you just shift all zeros in first, and that clears everything. Anyway, so you've got, this one line going over here, and you're not buffering, you're not having this. So I would definitely have another buffer chip on here. It could be as simple as that. I mean, that could solve all your issues right there. So yeah, definitely add a buffer chip. So as I said, it could be like a combination of factors, but you know, the main things I would do on this board is I would actually add an input buffer. I'd add a Schmitt trigger input buffer chip. You can either do like 2 inverters in series or just do a buffer, whatever you want to do. And then I would have drivers on here. You could use the same chip because you've got, what, 3 lines. There you go. You've got a 6 package. You can use the one chip. 3 can be your input buffer. 3 can be your output driver. So then you've got, so you're buffering the signal to drive it out powerfully to the next line. So you only have to drive that one segment. You don't have the one on your Raspberry Pi trying to drive this segment, this segment, this segment. You've got all the capacitive, and you've got the capacitance of the line, which gets more as you go along, and also the capacitance inputs of the loading of the chips. These aren't TTL chips, they're like CMOS chips. And, you know, so that could solve your entire problem. As I said, I'd add more bulk decoupling on here for your power devices. I'd probably, you know, you could like split your ground plane or whatever. For just keep those separate for your lower stuff, but that's not really neither here nor there. I don't expect that to be an issue, but I'd definitely put some extra, you know, a couple hundred mic bulk decoupling on there for those large current transitions. And then you've got things like, as I said, like why. Like this is designed, these are optocoupler inverters. You're already sharing the ground between this system and with the Raspberry Pi as well. So so you're using a common ground, but then you're doubling up on these optocouplers and these transistor arrays here. You're actually, doubling up on these boards as well, and on your schematic, and on here you got to have the extra chips to drive it, and it's driving all this current for no isolation reason. If you needed isolation in the system, sure, that's what these things are for, but you're actually sharing the common ground between all of your boards. Your Raspberry Pi going over here, and then I won't get into like common mode noise in the whole system and stuff like that. There's a whole nother thing, which is another reason to use Schmitt trigger inputs here as well. So yeah, I would, you could find just those buffers solves everything, and all your problems just magically go away. Yeah, and the other things I talked about, like differential pair driving and stuff like that, I wouldn't like do that for this design. I think this is probably good, but like fireworks, I don't know how far apart do these driver modules, if you're talking about like tens of meters, hundreds of meters, for example, then you're not going to be able to do this properly with a 5-volt single-ended 5-volt TTL type stuff. You're going to have to go for long differential pairs, or these days these new kiddies, they'd be using Ethernets and their ST arm micros and another problem, which almost certainly has something to do with it, is a voltage level translation. You said you're driving this with a Raspberry Pi. They're actually 3.3 volt signal level outputs, and this is being powered. It says, VCC, but it's 5 volt output apparently. So we have to go over to the data sheet over here, and let's have a look at the signal levels. High input voltage level, there it is at 4.5 volts. It's once again, it doesn't give a figure for 5 volts, but you're right on the margin there. So so if you're trying to drive a 5 volt CMOS device like this with a 3.3 volt drive, you're right on the margin of where it's going to do it. So you're right in the gray area there. Once again, you might find, as you have already found, it did actually work with one board, but then when you add an extra load on with the extra board, and boom, you're right out the window in terms of your voltage margin there. So you need a logic level translator. So you could, because the 595s, of course, can be powered down to 2 volts, you could actually have a 3.3 volt regulator on this board and actually power the 595s from 3.3 volts. And then the receiver level would be fine, of course, but then would the 3.3 volt output of the 595 be enough to drive the ULN 2803s? Well, we have to go over to the ULN 2803 data sheet over here. Like different, it's not really logic threshold levels like it is with regular CMOS. They call it VI, which is V in on, which is the on state, which is the output transistor saturated. So on state input voltage with VCE, or V collector emitter saturation voltage of 2 volts. So this varies. So the input voltage varies with how much output drive current you've got. So, but it's up in the order of, a couple hundred milliamps. You're only driving like, 10 milliamps with each one, or something like that, right? So it's NAF4. So it's got actually a maximum value of 2.4 volts, but even at 300 milliamps, it's 3 volts there. So you could actually drive this with, probably have. It looks like you can actually do it, even though it specifically says up here, operation directly with TTL or 5 volt CMOS devices. So, well, TTL is lower than that. The levels are quite low. So yeah, it looks like, yes, you could actually just drive these. You could actually have a voltage regulator on your board and receive everything at 3.3 volts. So you wouldn't need any logic translator. Otherwise, you still wanted to power it at 5 volts for whatever reason, then you could use a logic level translator, 3.3 volts to 5 volts. You can either get those as chips, or you can even do discrete transistor solutions and other stuff, but you just use an off-the-shelf chip. So yeah, it looks like that's possible. So that's certainly one of the issues here. And of course, that doesn't negate all of the other stuff that I've talked about. This is all part of the design review process. You might find, oh yeah, you simply, change add a 3.3 volt regulator, all your problems are fixed. But that doesn't mean that all the other stuff we've talked about is not potentially an issue. And then, of course, you've got your more professional things. If you wanted to, if you're really serious about this, you want to sell it perhaps, or you want to make hundreds of these things and actually, take it more seriously. You're talking about ESD, because you've got long lines on the input surge protection and stuff like that, power surge protection, all sorts of things. And then you've got RFI. For example, we talked about noise on the signals using the Schmitt trigger. One of the issues can be you've got big antenna leads on the thing, right? So it can be picking up all sorts of crap. So you might want RF beads on the input and, things like that. So there's a whole swag of stuff we could go into. If I sat down and actually made a list, it'd be quite substantial. So anyway, I hope that gives you food for thought here about some stuff to add to this design. And I'm sure there's stuff I probably didn't cover here. And I'm sure everyone will fill the comments down below with, oh, it's definitely this, add this, do this, and which is great. That's the whole idea of this. Because I didn't prepare notes or anything for this. I just turned on the camera and pressed record and started waffling. So, I might have, my stuff that just didn't pop out of my mind or whatever. But hopefully that's given you a reasonable direction to go in. But as I said, I could do a whole series of videos on all of the different issues in setting up this. This is why you might think this thing is just so easy to do, right? You've got a Raspberry Pi. You're just driving a very simple 595. A serial latch. It doesn't get much simpler than that. And it doesn't matter that you're using output transistor drivers here, but it's a simple application. But it brings in so much when you start talking about, long lengths of transmission lines, potentially common ground things and buffering of long lines and synchronization. It could, as I said, it could just be a software thing that you're not you're not setting up your data before you actually latch it. If you're setting up your data and your thing at the same time, it might work sometimes, and then you fart halfway across the room, it doesn't work anymore. So anyway, that's why I thought this is a pretty neat example of how system complexity can really get out of control. And we could really, if you do want me to do a specific video on a specific aspect of something I've mentioned here or something I've missed, please leave it in the comments down below. So if you liked that video and found it useful, please give it a big thumbs up. And as always, discuss down below in the comments or over on the EEVblog forum, where there's just thousands of some of the world's best engineers over there. They'll just happily, they'll just love this stuff. They eat this sort of stuff up for breakfast, and they'll help you out with your design. So I think it's pretty much the best place on the interwebs if you need help for stuff like this. So anyway, yeah, that was fun. Catch you next time.